only integer values of n are required. Okay, so in physical applications, n will be an integer. Okay, and also this equation can be solved in series of ascending powers of x and or in descending powers of x. Okay, this equation can be solved in series of ascending powers of x or descending powers of x. Okay, but you see, this is an important observation. The solution in descending powers of x is more important than the one in ascending powers of x. So, the solution in descending powers of x is more important than the one in ascending powers of x. Now you see the nature of the solution looks like this. Y equals to C1 Pnx plus C2 Qnx. We use some symbols here, Pnx, Qnx. Okay, what is it? Pnx is given by this. You see, here Pnx is given by this multiplied by this. This is the value of Pnx, which is, you see, a series in descending powers of x. It is x to the power n, then x to the power n minus 2, etc., etc. So, it is a series in descending powers of x. And Qnx is given by this. Qnx is given by this. Here actually Pnx is called Legendre function of first kind and Qnx called Legendre's function of the second kind. And you see Pnx can also be written in this form. That means if we use this summation sigma, that means sigma notation, then this series Pnx can be written as this. So you see Pnx can be expressed in as a series in descending powers of x and which can be rewritten in this form, which is actually, in this case, we use the summation notation, sigma notation. Here you see m, this m is n by 2 if n is even. What is it? Actually, m denotes the number of terms in this series. Yes, m denotes the number of terms in this series and that number must be an integer. So, if n is even, then m equals to n by 2, and if n is odd, then number of terms m is given by n minus 1 or divided by 2. So, here m denotes this n by 2 when n is even and m equals to n minus 1 whole divided by 2 if n is odd. Okay. So, Pnx is called Legendre's function of the first kind and Qnx is called the Legendre's function of the second kind. Okay. And now you see the solution of Legendre's equation is given by this. Just remember this. Actually, the deduction is not included here, but just see the nature of the solution looks like this. Y equals to C1 Pnx plus C2 Qnx, where C1, C2 are some constants and Pnx, Qnx are given by this, just this. And Pnx is called Legendre's function of first kind and Qnx is called Legendre's function of the second kind. And you can use summation notation, sigma notation to express this Pnx like this, where m is n by 2 if n is even and m is n minus 1 whole divided by 2 if n is odd. Now you see this Pnx is called Legendre's polynomials of degree n when n is 0, 1, 2, 3, etc. That means n is 0 or a positive integer. If n is 0 or a positive integer, then this Pnx is called, here you have observed that Pnx is called Legendre's function of the first kind. Here Pnx is called Legendre's polynomials of degree n, provided n is 0 or 1 or 2 or 3, etc., etc. That means 0 or a positive integer. Then Pnx are called Legendre's polynomials of degree n. Okay. Here it was Legendre's function of the first kind and now it is called Legendre's polynomial. You see, if n is 0 or a positive integer, then Pnx are called, Pnx functions are called Legender's polynomials of degree n, and this Pnx will be given by this formula which is called Rodrigues formula. Pnx may be written in this form and then it is called Rodrigues formula. And sometimes it is easy to remember the expression for Pnx, which is actually easy to remember, which is called Rodrigues formula. Now we shall prove this relation, which is called orthogonality of Legender's polynomials. Okay, you see, just you see minus 1 integral minus 1 to plus 1 Pnx equals to 0 if n is not equal to m. You see, Pnx, product of Pnx, and then you take integral minus 1 to plus 1, this equals to 0 if n is not equal to m. Now you see, the Legender's equation is this, already you have observed in this, yes, this is Legender's equation. So you see, actually, just you note this, the Legender's equation is given by this, and then you just remember the solution is given by this, and where Pn is given by this, Qn is given by this, and where, and if n is 1 or positive integer, then this Pnx will be called Legender's polynomial of degree n, and Pnx, if it is expressed in this form, then it is called Rodrigues formula. Okay. Now you see, orthogonality of Legender's polynomial, there that means if m is not equal to m, then this product equals to 0. Pnx integral minus 1 to plus 1 dx equals to 0. We first write down Legender's equation in this form, and now you see, you know, Pnx is a solution of the Legender's equation. Okay, Pnx is a solution of this equation means if y is replaced by Pnx, if y is replaced by Pnx, then this equation will be satisfied by Pn, because Pn is a solution of this differential equation, which implies if y is replaced by Pn, then this will be satisfied like this, like this. Similarly, if Pm, you see the integer now it is m. If Pm is a solution, then also this equation, if y is replaced by Pm, then that must be satisfied by this, and so we get this. Now you see, just some algebraic calculations will be done. Multiply this equation 1 by Pm, and then multiply equation 2 by Pn, and then subtract. Then what we get, you see, you will get this thing. Okay, and now you see, you are to integrate with respect to x between the limits of integration from minus 1 to plus 1. Just to integrate minus 1 to plus 1, minus 1 to plus 1, minus 1 to plus 1, you see, like this. Just to integrate over minus 1 to plus 1 throughout, then it looks like this. Now we just integrate, that means we compute the first term that is given by this. Just you have to integrate the first term, that means we have to calculate this term. Okay, you see, and then you see apply integration by parts. Okay, if we apply integration by parts, then it will be like this, and you see this first term will vanish because of this factor 1 minus x square. If you put the lower limit, then also this factor becomes 0. If you put the upper limit, then also the factor 1 minus x square becomes 0. So this term will contribute 0, and so this will remain unchanged, that is given by this. Okay, and now you see minus 1 to plus 1 Pn, you see, yes, this integral equals to this. Similarly, if you see, this is actually the first term, this is actually the first term, and similarly you just compare first term with the second term. What is the difference? Just you see, m is replaced by n is replaced by m. So we should not calculate this term separately, just we interchange m and n to obtain the value of the second term, to avoid the further, to save time actually. So we just calculate this term replacing n by m and m by n, that means interchange m and n. Then what we get, this will be m, this will be n, and looks like this. Okay, just we interchange m and n in 4 to obtain 5, because we see the if we compare the first and second term, you see first and second term, You see, you compare this first and second term, then only you observe that m and n have been interchanged. Okay, so just by interchanging m and n, we can obtain the value of the second integral without computing this integral separately, like this. Now, you use these values, that means 4 and 5 should be used in 3. We should put the values of these two obtained from 4 and 5 in 3, and then you will obtain this. Now you see these two are same but of opposite signs, so this will be cancelled. This term should be cancelled, and so we obtain this integral equals to 0, actually like this, and these are actually non-zero. This n is not equal to m, so this will be non-zero, so this integral pn dx equals to 0, and has proved. Another thing you see generating function. What is it? You see, you can show, it can be shown actually that pnx is the coefficient. Pnx means same pnx, that is collinear function of first kind. You see, same pnx symbol is same as before, which is collinear functions of first kind, and if n is 0 or a positive integer, then it is called Legendre's polynomials of degree n. Okay, now you see, it can be shown that if pnx is the coefficient of h to the power n in the expansion of this in ascending powers of h, okay, then that means this, just you see, in ascending powers of h, if we expand this in ascending powers of h, then pnx will be the coefficient of h to the power n. So it looks like this. Pnx is the coefficient of h to the power n in the expansion of this, okay, in ascending powers of h. You see, so this equals to this summation h to the power n pnx. What is it? Pnx is the coefficient of h to the power n. We see this has been expressed in ascending powers of h, and in that case this pnx is the coefficient of h to the power n, so we can express this equals to this. Okay, in this case we say this 1 minus 2x h plus h square whole to the power minus half is called the generating function for pnx. If it is generating function for pnx, then it should be written as this. This equals to summation h to the power n pnx, where h to the power n actually pnx is the coefficient of h to the power n. H to the summation h to the power n pnx, that means it is a series in ascending powers of h. This right side is a series in ascending powers of h, and pnx is the coefficient of h to the power n. Okay, you see, pnx is the coefficient of h to the power n in this expansion in ascending powers of h, and then it is called, this is called the generating function for pnx. Okay, now you see some problems. Actually, some algebraic computations will be done to solve these problems. Okay, first of all, you see, we have to show that p to m plus 1 0 equals to 0 and p to m 0 equals to this. If n is a positive integer, so you have written this. If n is a positive integer, we can write pnx equals to this. Now you see, it is a terminating series. Why? You see, gradually the degree of n decreases. This is n minus 2, this is n minus 4. So gradually the degree of x decreases. So it is a terminating series. And you see, n is a positive integer. So if n is odd, what happens? If n is odd, then n minus 2 is odd, then n minus 4 is odd, and the last term should be x to the power 1. Okay, if n is an even integer, then it is, suppose it is 6, then it will be 4, then it will be 2, after that it will be x to the power 0. X to the power 0 means actually the constant term. So if n is a positive integer, pnx equals to this, and then it will be a terminating series, because when n is even integer, it will terminate with the term containing x to the power 0. Gradually you see, if n is even, n minus 2 is even, n minus 4 is even, so always the even integer remains even because each, you see, this degree is n, and then next lower degree is decreases by 2, so the even integer will remain even throughout. And so the lowest even integer, it may be considered as 0 also. Similarly, if n is odd, suppose it is 5, then it will be x cube, then it will be x to the power 1. So the lowest power of x, if n is odd, then it should finish with the last term should contain x to the power 1. So we just separate into two. Okay, n is even, where this, you see the term within brackets should be given by this. Okay, just you see, observe very carefully, then it will be easy to understand what has, you see, you see, you see, this is n minus 2, this is n minus 4, etc., etc. So in the last term, if n is even, the last term should contain x to the power n minus n, that is 0. If it is n, if it is n minus n, say, to obtain x to the power 0, then the last factor, this should be n minus 1. This should be n minus 1, n minus 1. Okay, and so it looks like this. If it is n minus 1, it is x to the power n minus n. This is n minus 1. N minus 1 means it is 1 only. It is 1 only. And here, if you replace, you see, n minus n, that is 0, x to the power 0. Then the last term should be this. Okay, if n is even actually. Okay, and if it is a n, then it should be n minus 1, n minus 1, the last term, and it will be x to the power n, and f4 is replaced by, say, n minus 1, and then, sorry, n, so it is 0, x to the power 0, that is 1. And you see, the denominator should be like this in the last term. 2 fours up, 2n minus 1, 2n minus 3. So it will be 2n minus 1, 2n minus 3, up to 2n minus n minus 1, and 2, 4, 6 up to n, up to n. So the last term looks like this. Okay, actually you see, if it is 3, if it is 3, then the last factor should contain 2n minus 3. So if it is n minus 1, so last factor should be 2n minus n minus 1. Just to compare this, it is 3, it is 3. So if it is n, and it is 4. So if it is n, then it is n minus 1. It is n minus 1. So the denominator, this factor should be 2n minus n minus 1, like this. Okay, starting from 2n minus 1, 2n minus 3 up to, just you replace this 3 by n minus 1 to obtain the last factor. Okay, and you see, here you see in the first term there is only 1, 2, then 2 into 4. So in the last term it should be 2 into 4. Actually, what is your observation, that is important. You observe these terms carefully to write down the last term. And you see, since it is x to the power 0, so there is no term containing x. Actually, this is free from x. This is free from x, this term. So by putting x equals to 0, what has happened? Only this will be non-vanishing term by putting x equals to 0, because this term is independent of x. So Pn0 is given by this. Pn0 is given by this. Just to see the calculations, I have written each and every step. Okay. I think you may check these calculations. Is there any typographical error? I think you will check these steps very carefully. I have done each and every step. Will I repeat or proceed?
If you could repeat once, ma'am.
Okay. From where? From where?
Yes, ma'am,
From
from here.
here? Okay.
Yes,
Okay.
ma'am.
Okay. First of all, you observe that this term, how can we write this term? In order to write this term, we observe this series very carefully. Okay. You first observe if the term, suppose this term, which contains x to the power n minus 4, then what is the last factor? Okay. And you see, if it is 4, then it is 3, then also it is, this is n minus 3, 3 means 1 less than 4. Similarly, the last factor in the denominator is 2n minus, okay, this is same as, okay, same as this. These two are the same. Okay. And you see, gradually the degree of x decreases. This is n minus 2, this is n minus 4. So gradually the degree of x decreases. And so if we start with this even, suppose this is say 6, suppose this is 6, n is 6, then it is x to the power 6, then it is x to the power 4, then it is x to the power 2, after that it is x to the power 0, and then it will be terminated. Okay, and if n is odd, suppose it is 5, then it will be x cube, then it will be x to the power 1. So the last term should contain x. Now we start with this where n is even. So you see the last term should contain x to the power 0. And you see, if it is x to the power 0, so it should be n. To make this x to the power 0, this minus n minus n should be there. And if it is n, then you see it is n minus 1. Similarly, this will be n minus 1. And so the last factor in the numerator should contain n minus 1. Instead of 3, just you see, this is n minus 1, because here it should be n minus n. And if it is n minus n, that means 4 is replaced by n, so it should be 3, so it is n minus 1. Similarly, in the denominator it is 3, means n minus 1. So this actually these factors can be written by observing this series. Similarly, these factors can be written by observing the factors in the denominator.
Yes, ma'am.
Okay, now we proceed.
Yes, ma'am.
Okay. So by putting x equals to 0, you see the last term remains unchanged because this term does not contain x. This is free from x. So by putting x equals to, why you are putting x equals to 0? Because you have to obtain p2m 0. So here x equals to 0. You have to put. And also you see p2m plus 1 x, if it is x and where x equals to 0, here actually n is odd to m plus 1. I have already told you that if it is odd, if n is odd, suppose it is 5, n is 5, then x to the power 5 x cube, x to the power 1. So all the terms should contain x. And so if you put x equals to 0, then this series vanishes, because
Yes,
all
ma'am.
the terms contain x, and if you put x equals to 0, all these terms will vanish. And so you will observe that p to m 0, okay, no, not this, yes, x equals to 0, no term is free from x. This is the expression, you see the last term containing x, and all other terms also contain x, and if you put x equals to 0, then all the terms will vanish. You see here, actually, these are some algebraic computations. May I proceed to the next problem? All calculations I have
Yes,
done.
ma'am.
Okay, okay. So I just, uh, okay. Now you have to solve this problem. You have to show that this integral minus 1 to plus 1 x to the power m pn x dx equals to 0, where m is an integer but it is less than n. M is an integer which is less than n. Here we can use this Rodriguez formula. Already it is observed. Rodriguez formula is given by this, and now you see you have to integrate from minus 1 to plus 1 like this, x to the power m pnx. Now pnx is replaced by this here, pnx is replaced by this here, and now you see you can use integration by parts. Okay, just use integration by parts, and now you see the first term should vanish because of this limits. Okay, and then you see only the non-vanishing term is this minus this. Again you apply integration by parts here, and then you can obtain this by using integration by parts again actually. Okay, and next you will obtain this. Again the first term will vanish and only the second term will survive. Okay, and then it looks like this. And now we can continue this process m times. and then you will get just if you repeat this twice, then it is 2. It is 2 if it is repeated twice. We have repeated twice and obtained this. So if it is repeated m times, then what will you get? This is m, this is m, this is m, and so if it is m, then x to the power 0, and look, it looks like this. If it is repeated twice, there exist two factors. If it is repeated m times, then it should contain m factors. So m, m minus 1, m minus 2 up to 1. So it should be m factorial. Okay. Now you see, if x to the power 0 is 1, and then you again integrate from minus 1 to plus 1 like this, and again you see this will give 0 value. Okay. Just you obtain 0. Now you have to prove some recurrence relations like this. Pn equals to this. We have to prove P equals to this. You see, we can write this generating function. Already I have discussed this situation. Just you observe again. Generating function, I have told you, yes, this equals to this. Okay, where you see Pnx is the coefficient of h to the power n in the expansion of this in ascending powers of h. Actually, if you break this summation symbol, then it will be a series in ascending powers of h, and here this is called generating function for Pnx. Just we use this in this particular problem. Okay, you see, we have written this generating function for Pnx, and then differentiate with respect to h. Differentiate with respect to h, then you will get this. Okay, and multiply both sides by this factor. Then you see this is actually whole to the power minus 3 by 2. Then you multiply again this. If you multiply this expression by this factor, then it becomes minus half, because there is another 1 minus 2xh plus h squared. So if we multiply both sides by this factor 1 minus 2xh plus h squared, then it looks like this. Okay, now you see this actually the right side. You see x minus h into this equals to this 1 minus 2xh plus h squared equals to this n h to the power n minus 1 pn. Actually, you can replace this by this sigma h to the power n pnx. Okay, already it is discussed that this may be written as this summation h to the power n pnx. Now you just equate coefficients of h to the power n minus 1 from both sides. Okay, h to the power, you just see, you have to equate the coefficients of h to the power n minus 1 from both sides. You observe the left side, h to the power n minus 1. How to obtain? You see, this is x, h to the power n, pnx. So, if it is required to find the coefficient of h to the power n minus 1, if it is h to the power n minus 1, then this coefficient should be pn minus 1. So the coefficient of h to the power n minus 1 should be x into pn minus 1, just like this. And again you see in this term, if it is n is replaced by n minus 2, then h into h to the power n minus 2 will give you h to the power n minus 1. So if n is replaced by n minus 2, then also this n will be replaced by n minus 2. Then product of h and h to the power n minus 2 will give you h to the power n minus 1. So the coefficient of h to the power n minus 1, actually n is replaced by n minus 2, and when it is multiplied by h, it will give h to the power n minus 1. So n should be replaced by n minus 2. So it is minus pn minus 2. This is the coefficient of h to the power n minus 1. These are actually the coefficients of h to the power n minus 1 on the left. And right side, similarly, you see h to the power n minus 1, the first term, okay, it is okay, 1 into this, it is okay, but in the second term, since h is there, then we should take here h to the power n minus 2 to obtain h to the power n minus 1. So n should be replaced by n minus 1. This n should be replaced by n minus 1. This n should be replaced by n minus 1. Then it is h to the power n minus 2 After that, h into h to the power n minus 2 will give you h to the power n minus 1. And finally, you see, to obtain again h square into n, how to obtain h to the power n minus 1? So it should be h square into something that will make h to the power n minus 1. Then what will be this power? Should be n minus, what should be the power of h, so that h square into this will give n minus 2, right? Actually, if n is replaced by n minus 2, then this power should become n minus 3. H square into h to the power n minus 3 means h to the power n minus 1. So if n is replaced by n minus 2, this n is replaced by n minus 2, then this h to the power n minus 3 and multiplied by h square will give you h to the power n minus 1. So it should be n minus 2 and then it should be Pn minus 2 like this, which is actually the coefficient of h to the power n minus 1. Now, after simplification, it will be looks like this. It looks like this. Okay, if we equate the coefficients of h to the power n from both sides, then you will get, it will give this. So, in order to prove, you see, Pn to n minus 1 into x Pn minus 1 minus n minus 1 Pn minus 2, you see, we have taken this comparing coefficients of h to the power n minus 1. We obtain this. But if we equate coefficients of h to the power n from both sides, then you will obtain this. If it is required to prove this relation, then you have to you equate the coefficients of h to the power n. So, as per requirement of the problem, you have to decide which coefficient should be compared. Another problem, you see, we again start with this series, which is generating series, and then you differentiate both sides with respect to h, then you will obtain this. After that, differentiating both sides of 1 with respect to x. Here you see differentiate 1 with respect to h. In the second case, you see differentiate both sides of 1 with respect to x, and then you will obtain this. After that, you have multiplied both sides by x minus h. Why you have multiplied by x minus h? Just you see, here the left side contain x minus h into this factor. To make this term, you see x minus h into this factor, we have multiplied both sides by x minus h to obtain this. And then just compare 2 and 3 and we obtain this. Okay, and now we just break these summation symbols and obtain this. And then again you equate coefficients of h to the power n from both sides and obtain this, and then it is proved. And in order to prove Pn1 equals to 1, you see, we start with the same generating series, put x equals to 1, obtain this. You see, this is 1 minus h whole square, whole to the power minus half. So it will be this. And actually, you see, sigma h to the power n should be 1 minus h whole inverse should be maybe written as this. And then you see Pn1 equals to 1. Another, you see, to prove that Pn minus x equals to this, Pn minus 1 equals to this. We have this, again we start with the generating series. If you replace x by minus x, then you will get this. If you put h equals to minus h, then you will get this. And then equate coefficients of h to the power n from 2 and 3, then you will obtain this. Just to equate coefficient of h to the power n, from 2 it is Pn minus x, and in 3 the coefficient of h to the power n is minus 1 power n Pnx. Okay, then it is proved. And if it is x equals to 1, because we have to prove Pn minus 1, so put x equals to 1, then you will obtain this. Okay, some algebraic calculations are there. Okay, and I will send it, and you please check the steps thoroughly. Is there any typographical error or not? Okay, thank you. Just I stop sharing.
Hello, ma'am.
Tell me.
Yes, ma'am. Joined a little late. 2:40, ma'am. I think you missed my attendance.
Oh, sorry. ITB 64.
Yeah,
Who
no, ma'am. ITV 62.
62? What are you telling?
Yes, ma'am. I joined a little late, ma'am. I think I missed my
ITV
attendance.
62 joined late. I am checking. Acha.
Ma'am, civil 80.
Just a minute, please. ITV 64, ITV 62. Yes, I have given, and then civil 80, 80.
Civil 80.
Okay, just
And
So
ma'am,
ma'am,
ETB 042, ma'am.
80. Next.
ETB
Ma'am,
038.
ETB 042.
Just a minute, please. ETB 038
Yes, ma'am.
and another ETB 041.
Ma'am, ETB 042.
42, sorry, okay, 42. ETB 042. Any more? Any more? No. Thank you.
Thank you, ma'am.
Okay. Stop sharing.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Okay. Okay. I
Okay,
leave
ma'am.
now. Okay. I leave now.